Hello and welcome to this presentation by Imperas at DAC 2020, a virtual DAC. My name is Simon Davidman and I'm going to talk about Imperas' processor reference models, virtual platforms and tools. I'm going to start by giving an introduction to Imperas and focus on some of the issues facing electronic product developers, cover virtual platforms and simulation, introduce those, talk about Imperas' products and solutions, talk a little bit about the challenges of architectures and many core designs that designers are facing today, and focus on Imperas processor modeling and our RISC-V solutions before wrapping up. So Imperas, nobody today designs a chip without simulation, and we believe that that should be true for embedded software as well, and nobody should really be doing development of embedded systems without simulation. And Imperas, we focus on simulators and tools and modeling technology to help designers basically get their systems up and running and their hardware verified. We're over 10 years old, we're self-funded and profitable, we've got a UK-based team and other people in the US and elsewhere, and we focus really on processors. Our business model is that we charge for our tools. We're a commercial company. The majority of our revenue comes from tools and not services, and we charge for the licenses of the products and not the models. The models are free and open source using an Apache license, and we to facilitate this, about 10 years ago, we created Open Virtual Platforms as an initiative where there are public APIs and models in there for that. So it's all about trying to reduce schedules for embedded software developers to improve their quality, but also to enable hardware designers to explore design choices early and to verify their designs. Our key technologies are really in the software development area in terms of debug analysis and test. We provide accurate simulation engines using instruction accurate technologies. We have processor modeling methodologies and tools and technology and a library of processor models, and we have verification solutions for people who are building the RTL of their processors. So let's now talk about the issues facing electronic product designers. Well, trend over the last few years is that, yes, Moore's law gives you more gates, but you don't get any more performance, and more people are having more and more cores. And, people are putting hundreds of cores on their chips. And not only are they having more processors, but they've got more and more software libraries. For example, in the AI machine learning space, there's technologies like TensorFlow and Caffe and things like that. And all of these put requirements on the hardware platforms to challenge them to run better. And of course, there's more requirements too. For example, schedule. Everybody needs the product done sooner. It's got to be high quality and reliable. It's got all the security issues that everybody faces nowadays. It's got to be safe. Like, for example, you don't want people to be able to hijack it and with cars going off the road and things. So there's a lot of issues with software development, and more and more challenging. So in summary, there's more functionality needed. There's more software defining the products. There's more software libraries that are being used. You've got to have more and more processors. You've got to worry about reliability and security. So there's more and more challenges. And that's really where virtual platforms and simulation come in. Because what a virtual platform provides and what it allows is it gives you an environment where the software can be developed and run without it knowing that it's not running on hardware. And basically you build a collection of models that reflect the behavior of the hardware. The software executes on it, and it could be a single processor or multiple processors or multiple SoCs. It could be a whole board, it could be a whole system. There's no real limitations on that. And you run the same executables that you run on the hardware on these simulation models, and the models are typically written in C or System C. And you model the individual components, whether it's a Ethernet or USB, and you connect them up just like in hardware. And actually some of the components can talk to the real world. For example, our Ethernet device can read and send and receive packets across real Ethernet. So within the simulation, you can be browsing the web and stuff like that. USB, you can plug in a USB memory stick and access it from your simulation. And typically, instruction-accurate simulators can be really quite fast. So, for example, you build a system, you can run Linux up and have it running in under 10 seconds, which is often faster than embedded systems. And a lot of people use virtual platforms for testing, and actually it's a real complementary approach to a lot of people do hardware-based testing around FPGAs and things, but that tends to be expensive. And using a virtual platform, it can be an alternative to that. And people have typically done things like modify software to make it run on older versions of their products and things like that. But actually, virtual platforms provide a much better solution to this. They're cheaper than the FPGAs. They're more controllable. You get better visibility than even hardware boards, and it's easier to automate the development process in there. And of course, you can run all of your software stacks on them, whether it's the hardware or the virtual platform. And one of the things that virtual platforms enable is this modern development methodologies like Agile, where you've got continuous integration, whereas people check in their embedded software. You just run it on a simulation out in your data farm or the cloud, and then you can be building the product the whole time. You don't have to queue up and wait for hardware prototypes. You don't have to wait for FPGAs to be reprogrammed and things like that. So virtual platforms really enable this continuous integration for embedded systems. So now let's talk a little bit about Imperas solutions and products. So, success when you adopt virtual platforms, requires a lot of different things. It requires advanced tools, it requires methodologies, and it requires experience. And that's what Imperas provides. We have models, we have tools, we have a methodology, we have training, and we have resources in there. We've worked with some 60 customers over the last few years. We have the largest selection of CPU core models and other models in the library. We have several hundred peripheral behavioral models as well, and many existing platforms. And then on top of the models, we have all of the tools which allow you to develop the platforms themselves, or the simulate. You can develop the software, debug, and we have all these analysis tools on top as well. And we can also help people and under contract build models for people. Again, the models are open source, so that you can do what you like with the models that we develop. And so we can build models, we can build platforms, we can customize existing models, and we can help people build custom tools as well if they want to do specific verification challenges in the software or the hardware space. So we have the resources for that, and we have the ability to train, and we have also third parties that we can also work with to help you as well. So it's a very cost-effective and efficient solution when you work with Imperas on this. So talking a little bit about the environment. So at the heart of our technology is the models that we have of the processors, and we put those models in a virtual platform where we have obviously models of things like behavioral components as well, and that's the virtual platform put together. That runs on the simulation engine. You can bring in the test bench, you've got the application software on there, and then you can interact with different tools like the debuggers and the analysis tools in there. In terms of our tools in there, our debugger allows you to see inside not just the processor, but also the behavioral software and the platform as well. Our analysis technology is non-intrusive, so you don't have to modify any of the software or model source, and you can build your own tools in there. And the tools can work at different levels of abstraction. So yes, you can work at the lowest level and look at the instruction tracing and the registers and everything, but you can look at the functions tracing and how the OS is working, and even subsets, so that you can really choose at what level of abstraction that you want to drill down into your analysis and your design and do it. And so we have a variety of different tools, and it really allows you to accelerate the way that you develop things. In terms of models, we have a very large library of processor models. We have them, and they're written in C. They have System C interfaces around them. They can also run with System Verilog in there. We have models of all the ARM architectures. We have models of all the MIPS models. We have Renesas models, Synopsys ARC models, and more recently we've got a lot of the RISC-V. In fact, we have all of the RISC-V architecture, and I'll talk a little bit more about that later, including working with several vendors on that. And we have a lot of different processor models there. And we put the processor models with behavioral models together in platforms. We call them extendable kits, and we have about 50 off the shelf that you could download and look, and you can edit them and change them and make them be the way that you want them to be, and extend them, change the processors and things like that. So those come as all source again as Apache. We also have a technology, iGen, that helps in the building of these, where you put a description in a succinct script, and out comes the C code and everything that you need for your models. So based around a simulation engine of extremely high performance. It's a just-in-time code morphing engine, runs on the x86, and it maps the ARM or the MIPS or the RISC-V instructions on the fly to the x86 very efficiently. We have an API technology called Slipstreamer, which allows you to basically get intercepts so you can see what's going on when the instructions are executing, which allows us to extend and add tools. We have and build tools. We have our processor models based around the OVP technology, and we have a tool morphing technology which sort of brings it all together at runtime to make it extremely efficient. And we get hundreds and hundreds of millions of instructions a second, top speeds 5-6 billion instructions a second. There's a chart on the website, so you can have a look at that. You can boot Linux in under 10 seconds normally, pretty quickly there, and have full interactivity of it. And if you really need more speed, we have a technology called QuantumLeap, which is a parallel simulation accelerator, which takes the cores and takes the software that's running on the individual cores in the simulation and maps that down to the processors in the embedded system. It maps it down to the host processors that you're running on your desktop PC. So we have a variety of different solutions. We have the ability to model processors. So, you could build your own simulation if you want, and this is a make versus buy decision. But actually what we find is our customers find it's basically lower initial and ongoing costs and much better quality, because we have 100 years of effort into this modeling and simulation technology. We have many people that have used our technology. MIPS OEM'd our technology for the modeling all of theirs. Many proprietary companies have used us to simulate their processes and as reference and provide to their customers. We've had several ARM architecture licensees using us at the high end of sort of complexity. And we have, pretty much all of our RISC-V customers are building custom processors in there. Our technology is used early silicon, before silicon, for software development. We've had several people using it for the Mobileye and Intel and AMD have been using it to allows them to come to get the software up and running before silicon's available. People use us for software test to ensure the quality of their embedded systems. Several in the automotive space, several in the security space as well. And people can use this for doing sort of cycle approximate timing estimation, so that they can understand the performance of their technologies that they're building. And we worked in a project in the European Research Organization, a Safe Power, to analyze performance there. So sort of summary of our products here. So we have across the top is the different from a smaller product to a bigger product that we provide. We have a model library which comes with everything. Our generator comes with everything. And then the simulator, you can choose what level of complexity and performance that you want, including the parallel option. And we even have an option so that you can take the platform that you build and deliver it to customers as a sort of a fixed platform. We have so to move on to architectural exploration, most architectures today are getting very complex, from very simple multiple cores, where you might have scalar processes, maybe with something complex like vector extensions, all the way to on the right, where you've got complex arrays of processes, especially in the AI space, people with hundreds of cores, processes, and extremely complex configurations in there. So there's lots of challenges. And of course, our technology allows you to model that. And then on top of that, they have complex software architecture. This is an example of graph coarse bulk synchronous parallel VSP, which layers on top of it. And of course, the debugger needs to understand that and see how that's working. So we help in terms of solutions. We've got models of pretty much every processor that's standard out there. You can build your own or extend them. We've got a library of all this behavioral components, so you can add your own. You can build your platforms from it, and then we can simulate them at extremely high speed with an Eclipse-based multi-core debugger. You've got complete visibility, and you can see inside the platform as well as the software. And then on top of that, we layer on advanced tools, and we actually have a whole solution for hardware verification, working with the major EDA simulation vendors there. So now let's move on to processor modeling. So our processors model all that is in a processor in terms of what the software sees. So all of the register, all of the state, all of the behavior. What we don't tend to model is the sort of microarchitectural details like details of the pipeline and the caches and stuff. And we've modeled many ISAs. It's a complete proven technology here, including 7 proprietary ISAs, and several hundred models have been built. We have a flow to go to develop, like in the RISC-V world, there's custom instructions where you can characterize your application, develop new instructions, analyze it and characterize it, and then iterate around. And then when you're happy with it, then you can go on to check the performance of it and to document it, and then basically release it, check compliance and things like that. So we have all of the technologies there for developing that. So if we look at RISC-V, now one of the challenges in RISC-V is it's extremely highly configurable. So it does get pretty complicated, and actually it's many more than 60 questions you have to ask if you're designing a RISC-V processor. And so we have quite a lot of support for RISC-V here. So we have a simulator that we make freely available on GitHub. I'll talk a little bit about that. We have a test generator that we built, which is customer funded, so which actually allows us to develop test suites. And one of the suites we developed from using that is actually a huge vector test suite with over 7,000 instructions, many million lines of tests in there. We have a simulation derivative, a mutation testing tool, which allows us to see that values propagate in the test to the output, and that's extremely important for test quality. We have the ability, as I just showed, to add custom instructions. We work with other companies like Google, who have an instruction stream generator for generating RISC-V technology instructions for verification. We have a step and compare methodology, which allows you to verify in a system Verilog environment. So we have a free RISC-V simulator. It's available on GitHub, and it implements the full spec that's been ratified out there. We also have the vector and the bit manipulation stuff in and update it very regularly. We can take this model and use it in a system Verilog test bench. Here's an example where we're using sort of a step and compare methodology here. And when you do that, you get his example running with Cadence's system Verilog. So you get inside the Imperas debugger, you can single step, and then you can see all the waveforms as they're happening. So it's a very good verification environment with step and compare. And many people are using this technology, from Mellanox, which is now part of NVIDIA, to a Denso subsidiary. So there's several people in government funded or commercial. And at the bottom, you can see we have several partners, like, for example, Open Hardware and Chips Alliance, which are open source hardware organizations, and several proprietary companies as well. So we have a lot of people using our technology in the RISC-V world here. There's an example of the flow that Google have used, where they use our simulator as the reference here to compare against the RTL. So this is a flow that they've been using with the low risk processor core that's being developed in part of the Open Titan project. And actually there's a system Verilog functional coverage in there, and we've added vectors and bit manipulation in there, though that's not been released. Now, the Open Hardware group used the Imperas reference simulator as a golden reference in there to verify the RTL that they are developing. You can get also things like the coverage. That's an example of Mentor functional coverage coming out using it. And we have a collaborative design flow where we've been working with companies such as Andes, who use this as a reference, and Ultrasoc on the debug side of things, so that there are flows coming together between different companies in the RISC-V ecosystem. So to wrap up, our users benefit from by getting better quality by using our technology, reducing their schedules by using our technology, and reducing their costs using our technology. And some of the key technologies is the debugger and the analysis tools, exceptionally fast simulator, very large processor model library, and the ability for people to use it to model their own processors and enable them to use Imperas as a reference simulator for their verification. And our platforms provide complete controllability, observability, and repeatability, very easy to integrate into continuous integration environments. And then we have a whole bunch of other technologies to do with fault simulation, memory monitoring, OS-aware technologies. And the whole goal is to help people shift left. So again, summary, we have a variety of different products depending on functionality people need and the capabilities that they're looking for. So thank you very much for this. If you want more information, the link's there, imperas.com, send us an email, or at this virtual DAC, come along and talk to us and get a demonstration on our virtual booth. So thank you very much.